Yes. Is my screen visible to everybody? Somebody please respond.
Yes, sir.
Yes, sir.
All right. Today we'll start with the beams. Okay. So today we'll try to cover the derivation part of the beam, and in the next class we'll take a numerical, a very short numerical based on the beam. Okay. Let us start with the derivation part now. So I have, let us say, a simple beam. Okay. So let me draw a simple beam for you. Okay. So let us consider this is our beam. Let me make it straight. Okay. Let us assume that this is beam node number 1 and this is node number 2. Okay. Let us assume this is element number 1. Okay. So generally uh, we give the elements numbers to each and every member. As far as the axis is concerned, so let us assume this is your x-axis. Okay. So let us call this as your x-axis. Okay. And the origin of this axis is over here. Okay. So if that is the case, so your length of the member, so this will be the length of the member, and the length of the member, let us call this as L. Okay. Since this is a beam, there will be a deformation which will be there in the direction which is perpendicular to the axis. Okay. So let us assume this particular axis is like this. Okay. So this will be the axis where you will get the deformation, and since this is a beam, so we will call this deformation as W. Generally for bars we call deformation as U, and U is always parallel to the x-axis, and for beams the deformation is perpendicular or the transverse direction, so we generally call it, or we denote it by a symbol W. Okay. So this is the basic assumption. So now let us quickly see the derivation of the stiffness matrix for the beam element. Okay. The very first thing we need to assume over here is the displacement polynomial function. Okay. So if you remember, in the case of bar, we have assumed U is equal to A1 plus A2 x, or maybe U is equal to A plus BX. Okay, something like that, right? So here we are going to assume. Okay. So let us say, so this is completely based on a simple assumption that our displacement polynomial W is a function which is something like A1 plus A2 into x plus A3 into x square plus A4 into x to the power 3. Okay, so this is what I am assuming this, right? So if this is the displacement polynomial, then I can get the rotation value. Okay, so rotation value, generally it is denoted by a symbol theta, and it is generally calculated by taking a derivative of W with respect to x. Okay, so if you go for its derivative, so the d by dx of a1, it will be 0. D by dx of a2 into x, it will be simply a2, isn't it? So this will be a2, and this the second or the third section, it will be something like 2 into a3 into x. Okay, plus we have, this is 3 into a4 into x to the power 2. So this is the what you can say, equation for the rotation part, right? So if you consider a free body diagram, I have already drawn the free body diagram over here. So in this particular case, you have here W, and W will be called as W1 over here, and here this will be W will be called as W2 over here. Okay, as far as rotation is concerned, here theta will be called as theta1, and here the theta value will be called as theta2. Okay, as far as this x is concerned, this will be x, this will be called as x1, and its numerical value will be 0 because you have the origin over here. Okay, and in this particular case, the value of x will be called as x2, and its numerical value will be L, because we are assuming that the length of the member is from first node to second node, it is nothing but your L value, right? So now with this background, now let us continue ahead to find out what is the unknown constants. Okay, so what we can do is we can apply the boundary conditions over here. Okay, so let me write down over here, that is a apply boundary conditions. Okay, so now at the point number 1, okay, so here if you refer point number 1, at point number 1 we already know the values, that is when x equals to 0, the w value will be called as w1 value. Okay, so let me write down over here, that is at node 1, at node 1 the value of x will be x1 and its numerical value will be 0, and secondly the value of w will be called as w1 and its numerical value is not known to me. Okay, so what I'll do is I'll quickly name this as expression number 1 and let me name this as expression number 2. Okay, so if I substitute these values in expression number 1, okay, so if you substitute this in expression number 1, so your w will become now w1. So w1 will be something like a1 plus a2 and x value will be 0 plus a3 into the x value will be again 0 plus a4 into again x value will be 0. Okay, so this is my expression number 1. Okay, so let us call this as expression number, let us say a. Okay, small a. Similarly, if you substitute the same boundary conditions, okay, so we also know that at the node 1 the value of theta is called as theta1, isn't it? So if you substitute these boundary conditions in expression number 2, so expression number 2 will become something like theta1 equals to a1 will be 0 because there is no a1 term. Okay, the a2 value will be there as it is, plus you will have something like a2. Okay, this will be, sorry, a3, okay, into this will be 0, isn't it? Then here let me put 1 over here, okay, plus a4, okay, into 0 because there will be a 0 term. So here we have here you can see, here we have x term, here also we have x term, and here we don't have any x term over here. Okay, so because of that I'm writing the respective values over here. Okay, so we have one more expression, let us call this as expression number b. Okay, now let us substitute the boundary conditions which are there at node number 2. Okay, so at node 2 the value of x will be called as x2 and its numerical value will be L. The value of w will be called as w2, its numerical value is not known, and the theta value will be called as theta2 and its numerical value is also not known. Okay, so let us rewrite expression number 1 by using this boundary condition. So expression number 1 is basically w. Okay, so let us let me go slightly up so that you can see both. Okay, so your w, now this w value will become w2. Okay, so this w2 will be something like a1, okay, plus a2, and x value will be now replaced by L, okay, plus a3, okay, this L will be there, so this will be L square, okay, plus a4 into L to the power 3. So this is now expression number 1. Let us call this as expression number C. Okay, now let us rewrite the same thing for the displacement, sorry, the rotation part. Okay, so expression 2, this is the expression for the rotation. So your theta, so this will be theta2 now because we are at node number 1. So your a1 value, so a1 value is basically 0. Okay, there is no a1 value, so I am writing it like this. Okay, plus we have a2 value multiplied by 1 because there is no L term over here. Then I have a3 value, okay, and in a3 value we have a multiplication factor as 2 into x, so x now will be replaced with L. Okay, lastly we have a4 value, so a4 value is multiplied with a constant something like 3 into L square, okay, because there is a x square over there. So this is nothing but your expression number D. Okay, so basically what I have done, I have just substituted the boundary conditions in equation 1, which is the equation for the displacement, and the equation 2, which is equation for the rotation part. Okay. Now what I'm going to do over here is the expression which I have written over here, that is a1, oh sorry, not a1, expression 1. So this expression 1 I am going to write in a matrix form. Okay, so let me write down that. So this w expression, this is w is nothing but the deformation equation. So it was initially a1 plus a2x plus a3x square plus a4x to the power 3. Okay, so the same thing now I can write in a matrix form something like 1, this will be x, this will be x square, and this will be x to the power 3. This now can be multiplied with something like a1, a2, a3, and a4. Okay, I'm just rewriting the terms in form of a simple matrix. Okay, this is one expression, and you can also rewrite the entire expressions, that is expression a, expression b, expression c, and expression d in form of a simple matrix. Okay, so how we can do this? Let us quickly let me write down this. So your expression 1, expression a, expression b, expression c, and expression d, they can be written in this form, that is say w1, this will be theta 1, this will be w2, and this will be theta 2. Okay, so I can write it in this form, and here I'm just writing down the coefficients. So here we have 1, 0, 0, 0. Here you have 0, 1, 0, then 0. This will be 1, this will be L, this will be L square, and this will be L to the power 3. And lastly, we have something like 0, then 1, and this will be 2 times L, and this will be 3 times L to the power 2. Okay, and this now can be multiplied with the constants, unknown constant, that is a1, a2, a3, and a4. Okay, is it okay? Yes, students, is it okay?
Yes, sir.
Yes, sir.
Are there any questions as far as this part is concerned? Yes, students, somebody please respond.
No, sir.
Okay, shall I continue?
Yes, sir.
All right. So we have this expression now. Now here you see the value of w1 theta 1, w2 theta 2, they are not known. Okay, and a1, a2, a3, a4, they are just the integration constants, right? They are rather the constants of the polynomial. So we have to find out these constants also, that is a1, a2, a3, and a4. Now how to do this? Okay, the simplest way of doing this is we just have to take the inverse of this particular matrix, and then we can easily find out the unknown constants. Okay, so what I'm doing over here is we can take this entire matrix. Okay, this entire matrix on this side. Okay, just give me a couple of minutes. Just I'll be back. Just give me 2 minutes. Okay, so I'm back. Please pay attention on the screen. So now what I can do is I can get these unknown constants a1, a2, a3, a4 by taking the inverse of this matrix. So I have already calculated the inverse of this matrix. So I'm just writing down a1, a2, a3, and a4. So this expression now can be written in simple form, that is the inverse of this matrix. So inverse of this matrix is something like this. This is 1, 0, 0, and 0. This will be 0, 1, 0, and 0. This is minus 3 upon L square. This will be L. This will be L square, and this will be L to the power 3. Okay, the last row will consist of something like 0, then there will be 1, there will be 2L, and here we have 3L square. Okay, so this is the inverse of this original matrix. Okay, okay, and this can be multiplied with now a simple expression, that is W1 theta 1 W2 and theta 2. Okay, so this is how the expression can be solved, right? So now if you refer the earlier section, we have already calculated the value of W, or rather we have expressed the value of W in terms of matrix, which is like this: 1x, x square and x cube multiplied by a1, a2, a3, a4, right? We were not knowing what is the value of a1, a2, a3, a4, but now we have already calculated what is the value of a1, a2, a3, a4 in the form of this particular expression. Okay, so now what I can simply do is I can rewrite this entire expression into a simple form. Okay, so let me go down over here. So earlier I was having small w. Okay, so now this can be rewritten as 1x, x square and x to the power 3, okay, multiplied by this entire thing. Okay, so this entire portion, this will remain as it is over here, and this will be now w1 theta 1 w2 and theta 2. Okay, so I'm just writing down a cross symbols over here. The values will remain same. Okay, same as the matrix which are over here. Okay, so now you see earlier the value of w was depending on what is the value of x, okay, and what are the constant value. But now if you see the value of w, it is depending on the nodal displacement. Okay, so w is now depending on what is the value of w1, what is the value of theta 1, what is the value of w2, and what is the value of theta 2. Okay, so the product of this, okay, so here you say this is w, and here this entire thing, okay, the product of this matrix, this is called as shape functions. Okay, so this is called as shape functions. So this w now can be replaced by something like n1, this n2, then n3 and n4. Okay, and multiplied by, you have this will be w1, okay, theta 1, w2 and theta 2, not theta 3, theta 2, right? So this is nothing but the shape function. You can also write the same w in form of like n1 w1 plus n2 theta 1 plus n3 w2 plus n4 theta 2. Okay, we can write it in the both way. Okay, now let us quickly see what are the values of n1 and n2 and n3 and n4. Okay, so here n1. Okay, so n1, if you observe carefully, let me just slightly go down. So n1 is basically a product of this matrix, okay, this, okay, multiplied by this vector. Okay, when I say this vector, if you refer the values over here, so it is nothing but your this vector, isn't it? Because the matrix are same, isn't it? So if you go for the multiplication of these two matrices, so here n1 value comes out to be something like 1 minus, this will be 3 upon L square into x to the power 2 plus 2 divided by L to the power 3 x to the power 3. Is it correct? Yes, somebody please respond. Is it correct? बराबर है? Yes, student, is it correct? Multiplication.
सर एक्स क्यूब की टर्म जीरो नहीं आएंगी?
सॉरी,
एक्स क्यूब की टर्म
हाँ
जीरो है ना सर, लास्ट -3/L स्क्वायर, उसके नीचे जीरो।
एक सेकंड रुको, मैंने शायद गड़बड़ करी है, सॉरी। आई थिंक आई हैव
इनवर्स रॉन्ग है क्या सर?
इनवर्स में गड़बड़ किया मैंने, जस्ट वेट अ मोमेंट। ये जो इनवर्स की वैल्यूज है ना, वो आखिरी वाला रो मैंने गड़बड़ लिखा है, जस्ट प्लीज लेट मी करेक्ट इट। ओके, शायद मैंने ये भी गलत लिखा है। एक्चुअली दो मैट्रिक्स लिखे थे ना, तो बिकॉज ऑफ दैट आई हैव मेड सम मिस्टेक। एक्चुअली दिस इज -2/L, this is 3 upon L square, and this is minus 1 upon L. Okay, so that's my mistake. I'm very sorry for that. This is 2 by L to the power 3. Okay, this is 1 divided by L square. Okay, this is minus 2 upon L to the power 3, and this is 1 upon L square. I think this is correct now. Okay.
Yes, sir.
Okay, so that was a mistake from my side. Okay, anyway, so just see whether you are getting the correct values or not, and ultimately what you are going to get is this n1. Okay, so this is the value of n1. Let me write down the value of n2 also now. So n2, so now if you want to take the n2 value, so all we have to do is take a product of this matrix. Okay, the same matrix, because your this x1 x1 this and this, it will remain same, and this will be multiplied with this particular row or this particular column. This column is nothing but this column. Okay, this one. So similarly, now you can write the value of n2 also. Okay, so your n2 value comes out to be something like x, okay, minus, this is 2 upon L into x square, okay, plus 1 upon L into x to the power 3. Okay, please somebody cross check whether it is correct or not. Yes, students, please cross check.
So 1 upon L square.
1 upon
L square into x cube. So inverse.
Just a minute. Yeah, 1 upon L square, correct. Correct. Okay. Now, similarly, we can have the value of n3 also. Okay. Just please do the calculations. I'm just writing down the value of n3. You please cross check this. So this is something like 3 by L square into x square. This is minus, this is 2 upon L to the power 3 into x to the power 3, and your n4, that is shape function, this is 1 upon L square x to the power 3 minus 1 upon L x square. Is it correct? Somebody please cross check.
Yes, sir, correct.
Both are correct?
Yes, sir.
Okay, great. So these are nothing but the shape functions, right? So now let us see the variation of the shape function across the element, right? So if you see the variation, let me start with the n1 value. Okay, so let us say this is my element. Okay, and I have this is my node 1 and this is my node 2. Okay, so let me put a circle over here, and the length of the element is basically L. Okay, so here the value of x will be 0, and here the value of x will be L. Okay, so now in this n1 expression, if you substitute the value of x as 0, okay, so here if you substitute this as 0, then what is going to happen? The n1 value will become 1. Okay, so your n1 value is 1 over here. Okay, and in the same expression, if you substitute the value of x as L, okay, what is going to happen? Somebody please tell me. क्या आएगा? What will be the value of x? 0. Okay, so this is going to become a 0 value. Okay, so here this will be 0 value. Okay, so now I have to join this point, okay, which is 1 over here, and this is 0 over here. So what kind of curve should I draw? Is it straight line or second degree curve or third degree curve? Yes, bolo. Yes, anybody? So it's a third degree curve, because you see x to the power 3 is there. Okay, so here if I draw a third degree curve, it looks like this. Okay, I should use a different color so that it should be clearly visible. So it looks like this. Okay, it is going down, and then it is going like this straight line. Okay, so this is the variation of this expression. You can even plot this expression in Excel. You will get a variation which is something like this. Okay, so this is very much similar to a fixed end beam, or a beam which is having both end fixed, and one end is displaced by a single unit. Okay, and if you move it by 1 unit in the x direction, so you will get a variation which is something like this. Okay, so this figure you might have seen in the matrix method, especially in the derivation of the stiffness matrix of a beam element. Okay, now similarly, I am not going for n2 now, I am just going for n3 in place. Okay, so let me plot a variation of n3 now. Okay, so n3, it basically n3 is if you see the value of n3, so n3 is multiplied with w2. Okay, n1 is multiplied with w1, n2 is multiplied with theta 1, n3 with w2, and n4 with theta 2. Okay, so in this particular case, what I'll do, let me substitute the value of x as 1 and 0 and 1. So here this will be node number 1. Okay, here this will be node number 2, and here the value of x will be 0, and here the value of x is L. Okay, so what I can do is, in place of this x, if I put this value as 0, okay, so what is going to happen? N3 value will be, of course it will be 0, isn't it? Okay, so here this will be 0 value. Okay, but now if you substitute the value of x as L, okay, can anybody tell me what will be the value of n1 n3 now? Yes, somebody please tell me. 1. So here you have the value of n3 as 1 over here. Okay, so here it will be 1 and here it will be 0. And how should I connect this? Straight line, second degree or third degree curve?
Third degree curve.
Third degree curve, very much similar to the variation of n1. Okay, so let me use this one. So it will look something like this. So if you plot a variation, so it will go like this. Okay, and then it will reach somewhere over here. Okay, so this is very much similar to the beam which has both end fixed, but now the displacement or unit displacement is applied at the other end. Okay, so this shows the variation of the n3, that is the shape function. Okay, now let us quickly see the variation of n2 and n4. Okay, so if I plot same kind of a figure over here. Okay, so just let me put it over here. So I will call this as node number 1, this as node number 2. So here the value of x will be 0, and here the value of x will be L. Okay, so now what will happen if I substitute the value of x as 0 in n2 expression? Can somebody tell me what is the value of n2?
0.
Okay, so this is 0. Okay, and in the same expression, if you substitute the value of x as L, what will be the value of n2?
Minus L.
Sorry?
Sir, minus L.
Minus L, no.
0.
Sir, 0. Yes, sir, 0.
It should be
0.
Okay, so this should be 0. Then if both ends are 0, how should I join this? Isn't it? So it should not be joined with a straight line, because you know that the degree of this particular expression is 3. Okay, so it's a third degree expression. Okay, so what you have to do is you have to plot the intermediate points. Okay, if you plot the intermediate points, then and then only you will be able to see the variation of the n2. Okay, so if you see the variation of n2, so it will look like this. Okay, so it goes like this. Okay, sorry, let me draw with red color. Okay, so it goes like this. Okay, and then it goes like this, and then it goes something like this. Okay, so this is very much similar to a unit rotation which is applied at node number 1. Okay, so the variation of n2 is something like this now. Okay, so now similarly you can even plot the variation of n4 also. Okay, so let me draw a straight line over here. Okay, let me put a black line. Okay, so this is the case, and here I'll be having node number 1. Okay, I'll be having this as node number 2. Here the value of x is 0 and here the value of x is L. Okay, so in this particular case also, if you substitute the value of x as 0, so n4 value will be 0, and if you substitute the x value as L, the n4 value will be also 0. Okay, so if you plot a variation of this, so you need to have what you call it as intermediate points, then and then only you will be able to get the correct variation. Okay, so if you plot an intermediate point, so you will be getting a variation which is something like this. Okay, so it goes like this. Okay, and then it goes like this. So basically here the rotation is applied at the other end. Okay, and here if you see, the rotation is applied like this. Okay, in this particular case the displacement is applied like this. Okay, and in this case the displacement is applied like this. Okay, so you might have studied a similar kind of a approach in the matrix method where the unit displacements and unit rotations are applied. So this is very much similar to that one, and in this way you can get the variation of the displacements, variation of the n1, n2, n3 and n4. Okay, now as far as the basic rules are concerned, the summation of n1, n2, n3, n4 should be 1. So this is not applied over here because we have n2 and n4, they are related to the rotation. But if you consider n1 and n3, so if you add n1 and n3, you will always get 1. Okay, because they are related to the displacement part. Okay, so in this way you can get the variation of the displacement. Okay, is it clear to everybody? Are there any questions as far as this part is concerned?
So n2 plus n4 is equal to 0 नहीं हो सकता क्या?
नहीं होगा, actually that is related to the rotation part. Only for the displacements, the n1 and the shape functions which are related to displacement, the sum is always 1. Okay, and if you remember, like if any value is 1 at one end, at other end the value of n will be always 0. So this is not the case with this n2 and n4, because you see the value of n2 and n4 at node number 1 they are 0, at the same time node number 2 is also they are 0. Okay, so that should not happen over here. Okay, so it is applicable only when you are dealing with the displacements only. Okay, yes, is there any other question? Okay, shall I continue then? Yes, all right. So let us quickly see the derivation part. So if you remember, usually what we do is, to generate the stiffness matrix, we go for K elemental is equals to integration over the volume. We have V transpose into D into B over dV. So this is a generalized expression which is derived from the equation of minimum potential energy. So for this purpose we required B value. Okay, so B is nothing but your strain displacement matrix. Okay, so for this purpose we need to calculate the strain, right? So in case of beam, we are already familiar with the expression, that is M equals to minus EI, then we have d square W by dx square. I think everybody is familiar with this. Okay, so here this d square W, or rather in this particular case the value of strain or the value of stress is generally denoted by M. Okay, the value of strain is nothing but minus d square W by dx square, and the D matrix. Okay, so this is nothing but stress strain matrix. In case of beam it is written as EI. Okay, so now coming back to the original derivation part, so we have already seen the value of W. Okay, so W was nothing but something like N1, N2, N3 and N4 multiplied by, we have something like W1, theta 1, W2 and theta 2. Just now we have seen this. Okay, so this is the variation of the displacement. Okay, so now all I have to do is I just need to go for the strain. Okay, so strain is nothing but minus of d square W by dx square. Okay, so d square W by dx square, this can be calculated by taking simply multiplication of this. So I can directly write down over here, that is strain equals to minus d square W by dx square. Okay, this can be written in the simplest form, that is d square by dx square of n1. Okay, n1. So then d square by dx square of n2, then d square by dx square of n3, then d square by dx square of n4 multiplied by, we have w1, theta 1, w2 and theta 2. Okay, so all I have to do is I just have to go for a derivative of this n1 two times. Okay, and then this entire matrix. Okay, so uh, this entire matrix will become now B matrix. Okay, so B is nothing but strain displacement matrix, where you have strain on one side and you have the displacements on the other side. Okay, so let us quickly take a derivative of each and every uh, uh, n1, n2, n3, n4 two times. Okay, so we already have something like n1 value. So n1 value, if you remember, it is something like 1 minus this is 3 by L square into x square. Okay, plus this is 2 upon L to the power 3. Okay, into x to the power 3. Okay, so now if you go for d by dx of n1, so if you take this, so this will become 0 plus, oh sorry, this will be minus, not plus, minus this will be 3 upon L square and this will become 2x. Okay, this is 2 upon L to the power 3, this will become 3x to the power 2. Okay, then again if you go for derivative, so d square by dx square of n2, so this will remain 0 as it is, and this will become something like minus 6 upon L square. Okay, and this x will become now simply 1. Okay, plus this will be 2 into this will be 6 upon L square and this will become 2x. Okay, so finally what you can have something like this is, if you write this, so this will be something like this is minus 6 upon L square plus this is 12 upon L square into x.
Okay,
Sir,
L cube.
L cube.
Sorry, L cube.
L cube.
My mistake. L cube. Okay, so this is the first term, that is d square. I think I have made n2 over here by mistake. Okay, this should be n1 also. Okay, so this will be the first term of the B matrix. Okay, so similarly you can have a derivative, that is d by dx square. Okay, this will be n2. So this value, can somebody tell me what is this value, please? Okay, please let me the values, let me know the values.
So minus 4L by 4L plus 6x by L cube n2 value.
4 upon L
Minus 4
minus
upon L. Minus 4 upon L plus 6x upon L cube.
L cube or L square?
L square.
L square. Okay, I am not writing minus sign because ये यहाँ पर ऑलरेडी माइनस है, देखो यहाँ पर. ओके ओके, हाउ अबाउट दिस वन?
सर तो n1 की इक्वेशन में भी माइनस आएगा ना सर, माइनस चेंज हो जाएगा ना.
हाँ, तो ये अभी इसको चेंज करना पड़ेगा ना, इसको माइनस लिखेंगे ना
सर. ये -4L था ना.
हाँ हाँ, तो इसको मैं -1 से मल्टीप्लाई करूंगा ना बाद में. ओके, सो ये क्या हो जाएगा, ये हो जाएगा 6 अपॉन L स्क्वायर, बराबर है, एंड दिस विल बी -12 अपॉन L क्यूब x. ओके, ठीक है. अभी इसको माइनस से मल्टीप्लाई करके ही बताओ, फाइनल बताओ मुझे, so that I can put it in matrix form.
सर 12.
Sorry,
12x by L cube.
Okay, so let's
माइनस
write down. माइनस और प्लस आएगा ये.
सर प्लस
हाँ,
12
प्लस आएगा.
12x by L cube
12 upon L cube into x, and this will be, I suppose, minus
माइनस यस सर
6 by L square.
L
बराबर है.
square यस सर.
ओके. लास्टली कितना क्या आएगा ये?
सर 2 by L
ओके.
माइनस 6 by L square into x.
ओके, ठीक है ना, बराबर. आई हैव ऑलरेडी रिटन दैट. ओके, so basically your strain. Okay, so I'm just writing the entire portion one more time. Okay, so this is something like this. So your strain, okay, so this is your strain, is a product of your B matrix multiplied by your delta matrix. Okay, that is the displacement matrix. So the same thing now can be written in a simplified form as this will be the first term. So this will be 6 upon L square minus 12 upon L cube into x. Okay, so this will be the first term. The second term will be 4 upon L minus 6x upon L square. So this will be the second term. And the third term will be something like 12 upon L to the power 3 into x minus 6 upon L square. So this will be the third term. And the fourth term, just now we have calculated. So this is 2 upon L minus 6 upon L square. Okay, so this is the fourth term, and this will be of course multiplied with W1, theta 1, W2 and theta 2. Okay, so this particular entire matrix is nothing but your B matrix, that is the strain displacement matrix. Okay, so now coming to the derivation part. So we already know that the stiffness matrix K is integration over the volume. So this is B transpose into D into B over dV. Okay, so if you see, this is your B matrix. Okay, so this is your B matrix. So your B matrix is having 1 row and 4 columns. Okay, so here I can write this as integration over the volume. Since this is transpose, so all these value, 1 value, 2 value, 3 value, 4 value, it will come like this. Okay, and your EI term, okay, or the D term will be replaced now with a simple EI term. Okay, so this will be E and I. Okay, because your D matrix is your B EI term, and your B value will be something like this. Okay, this entire expression. Okay, and dx. Okay, oh sorry, this will be dv. Earlier we can write this as dv, but since we are going for the beam derivation, so this will become, in place of dv, now this will become dx, and this will become over the length. Okay, this is over the length and this will be dx. Okay, so here you see, this is a matrix which is having 1 column and 4 row. This is a matrix having 1 row, sorry, 4 rows, sorry, 1 row and 4 columns. Okay, this is, I think I have written reverse way. Okay, so I have 4 rows and 1 column. So the product will be 4 rows and 4 columns. Okay, so finally what you have to do is you just have to go for the multiplication part, and at the end of this multiplication, what you are going to get is something like this. So this is 12 EI upon L cube. Okay, this is 6 EI upon L square. Okay, ये मैट्रिक्स तुम लोगों को याद होना चाहिए, isn't it? Minus EI upon L cube. Okay, and this will be something like 6 EI upon L square. Since it is a symmetric matrix, so this will be minus 6 EI upon L square. This is minus 12 EI upon L cube, and this is again minus, sorry, this is plus 6 EI upon L square. Okay, here we have 4 EI by L. Okay, this is minus 6
सर सेकंड रो का फर्स्ट जो पॉजिटिव है सर,
सेकंड रो का
फर्स्ट कॉलम, हाँ सेकंड रो फर्स्ट
oh,
कॉलम
this is
पॉजिटिव।
positive, right. This is not there, na? Okay, thank you. And this is something like 2 ei 2 ei upon L. Okay, I hope this is correct now. And this is 2 ei upon L. Then this diagonal is 12 ei upon L cube, and this is minus 6 ei by L square. This is minus 6 ei by L square, and lastly this is 4 ei upon L. Okay, so this is the matrix. Okay, so after doing lot of calculations, you will end up with the same matrix which you have already seen in the first semester in the matrix method subject. Okay, I hope this is clear to everybody. Yes, students, is it okay? Are there any questions, please? Okay, then इसके बाद की story same है. Whenever you have to solve a problem, you have to use this matrix. You have to find out the effective load vector. Okay, and then using the basic steps of finite element method, you can solve the problem. Okay, so in the next class, probably we will take a simple problem. Okay, and we will see how it can be, how a simple beam can be solved using the finite element method approach. Okay. Okay, then let me stop the recording. Are there any questions meanwhile?